This is practice test 2, problem number 10. The energy of a quantum mechanical harmonic oscillator with frequency nu, the Greek symbol nu, is always a multiple of h nu, where h is Planck's constant and nu is the frequency, and is given by the expression E sub v is equal to, open parentheses, v plus 1/2, close parentheses, quantity times h nu. And where v is a type of quantum number, can take on values 0, 1, 2, 3, etc., etc., integer values. And what the question is, what multiple of h nu is the A? V equals 0 mode. Well, this is to illustrate how, I really like this example for this. When we do quantum mechanical, if we do a quantum mechanical calculation at this level, it's that simple. It's really going to be small numbers. It really corresponds to knowing what the numbers represent, more than being able to manipulate things. And if we are going to manipulate numbers, they're going to be little bitty numbers. So if v equals 0, E sub v is going to be equal to 0 plus 1/2 times Planck's constant times nu, and therefore, which is equal to 1/2 Planck's constant times nu. So therefore, 1/2 is the multiple of h nu. And this corresponds to the 0-point energy. For the fundamental mode of vibration. So this is not 0. This is going to be a non-zero energy, which depends upon the frequency, but it's non-zero. That's the ever-loving point. This is called the 0-point energy, and it corresponds to, if I have, like a guitar string, this is the fundamental wave. And this is a standing wave solution. The harmonic oscillator, like a guitar string, would vibrate like this. And the energy is going to be non-zero. It gives us a 0-point energy. We'll be talking more about that later. Now, for the second case, E sub v, where v equals 2, is equal to 2 plus 1/2 Planck's constant times mu equals, in this case, that's going to be 5/2 Planck's constant times mu. Therefore, the multiple is 5/2. And for v equals 3, as we have here, we just plug a 3 in here. Now 3 plus 1/2 is going to be 7/2. And so note that the difference between the energies of 2 is going to be a multiple of h, Planck's constant. So that when we space them in energy, okay, so therefore the multiple is 7/2. And that answers the question. But what we end up with is, for our harmonic oscillator, we have a series of lines. And this is the energy for the harmonic oscillators, and this is 1/2. And this is 3/2, 5/2, 7/2, etc., etc. And this corresponds to, this would correspond to the fundamental standing wave, the first harmonic of the standing wave, the second harmonic of the standing wave, this would be like my guitar string, plucking the open string. This would be pushing down, this would be the first octave above it, 2 octaves above it, 3 octaves above it. They're all separated in energy by h. The difference in energy here in each case is Planck's constant. In fact, this is how Planck did the whole thing in reverse. He solved for this value. This is the value he found as Planck's constant, which is the separation between these quantized harmonic oscillations. So and so that quantum condition that they're restricted to standing wave solutions was what gave rise to Planck's constant. And in practice, it's this simple. When we go to understand these things, it's this simple. It's just like, okay, plug in whatever value of E there is, and